Good morning, everyone. My name is Duarte. I'm a software engineer at ScyllaDB, and I'll be talking about our database. So I'll start with a brief overview of how the system looks like, and then I'll go into some implementation details of what exactly makes ScyllaDB tick. So ScyllaDB is a clustered NoSQL database compatible with Apache Cassandra, but it has 10 times the performance in similar hardware at predictably lower latencies, especially the higher percentiles. We are compatible at the API level, which means that there is no driver that's Scylla specific. You use all of the Cassandra drivers to talk with Scylla. And this also means that you can use Scylla as a backend for things like Spark or Presto or TitanDB, and it will work as if it were Cassandra. We are also compatible at the file format level, which means that you can take all of your Cassandra data files and put them in Scylla, and everything will work as expected. Another important thing is that we are self-tuning, and this means that we don't have a lot of tunables that you have to configure to get good behavior out of the system. We'll do that for you. For example, there's no setting to specify how large a mem table has to get before we flush it to disk. That depends on the load, and we decide for ourselves what that best value is. And finally, it is written in modern C++ with a lot of attention to the underlying hardware. So this is a fairly well-known benchmark. It shows, it compares a 3-node Scylla cluster against different Cassandra clusters of different sizes. And in the graph below, we can see that Scylla is competitive, a 3-node Scylla cluster is competitive with a 30-node Cassandra cluster. And if you look at the top graph, you can see that the 3-node Scylla cluster has much lower latencies than the 30-node Cassandra cluster. There are other independent benchmarks that are all online that confirm these results. Okay. So at the system level, like Cassandra, we are a Dynamo-based database, which means that no node is special. Any node can answer any request, and that node will act as a coordinator and will contact whatever replicas it needs to satisfy a request. We are available under network partitions like Cassandra, which means that data between replicas may diverge, and we need to run an anti-entropy repair to reconcile data. But it's very similar to Cassandra. And the data model is again that of Cassandra, and data lives in tables which have a well-defined schema. Data in a table is divided into partitions. A partition is the unit of distribution, so to speak. There's a partition key that identifies the partition, and we run that partition key through a function to obtain a token that will decide in which replicas that data will live in. A partition is itself divided into rows, each row identified by a clustering key. So a primary key is a partition key and a clustering key, and it fully identifies a single row. On disk, data is ordered by primary key, not by the value of the partition key, but by the value of the token, and then by the values of the clustering keys. So on disk, when we accumulate updates in memory, and at a certain point, we flush them to disk. And on the disk, the data is laid out as a SS table, a string sorted table. And these files are immutable, which means that if you add a value to a particular column in a particular row in this SS table, then if you want to update it, you don't update it in place. What happens is that you do a new write with a newer timestamp to replace that value. And that update is going to be held into memory until it will be flushed at a later time. So now we have two SS tables that contain a value for the same column in the same row. If I want to delete, I'm not going to, again, change that value in place in both of these SS tables. What we do is that we are going to add a tombstone, and a tombstone is a logical delete. So again, we are going to hold that tombstone in memory, and when we need to, we're going to flush it out to disk, to a new SS table. And this keeps going on and on. And as new files are created, the read performance is going to degrade. Okay, this file format or this structure is optimized for writes. If I have to do a read, for example, a scan over the whole table, then I have to read all of these files and look into them, and that's going to be expensive. So what's going to happen is that in the background, we're going to start a compaction process that is going to take a set of SS tables and compact them together. So if those 3 SS tables each held an insert, an update, and a delete for the same value of the same column, the same row, then that value is going to be absent from the compacted SS table because they're all collapsed together. And this process is very efficient because the files are sorted. So I just have to go and compare them and merge them together. And this is happening in the background, while at the same time we keep creating new SS tables. But once I have that compacted SS table, then a new read doesn't have to look into 5 tables, it only has to look into 3 tables. Okay? But the cost to optimize for the reads is that we need to have this background process. So this is how the request path looks at a higher level. So in memory, we have those mem tables I was talking about, which hold the updates for a period of time, and then are flushed to disk. This is sufficient to satisfy reads, but not for the writes themselves. Because if I have a lot of writes that are in memory, and if the node crashes and goes down, then we would lose those writes. So like a typical database, we have a write-ahead log in front of the mem tables, where we write, it's an append-only file where we write the write, and in case of a crash, we just have to replay that log. So this is it for the overview, and these are the same algorithms that Cassandra uses. And while it is important to choose a good algorithm, the implementation is also very, very important. And it's from the implementation that we get that 10x performance boost. Okay? So with that in mind, we have 3 implementation goals. That of efficiency, meaning that each cycle should count. And this is fairly easy to achieve. It's just optimization. Then we have utilization, where we want to fully utilize the hardware that we have. That means using all of the CPUs, using all of the memory, using all of the disk bandwidth, and all of the memory, all of the network bandwidth. This is something many applications struggle with. Some applications, no matter how much load you throw at them, are never able to fully utilize, for example, the CPUs, either because they have very few threads or because they have too many threads and have lock contention, for example. And finally, and most importantly, we want to have control over how those cycles are spent. And this is actually the key to achieve good latency, because we are able to prioritize online requests, like user reads and writes, and throttle down background processes like compaction. So underlying Scylla is the Seastar library, which is an open source library that we wrote for high performance C++ applications. And it imposes a thread per core design. So if you're using Seastar, you are going to have exactly 1 operating system thread per CPU core. This means that the thread cannot block ever, because if it blocks, then there's a CPU that's not being utilized. Okay, there is nothing else to schedule on that CPU. So this implies that we can't really have any blocking synchronization. And indeed, what happens is that we partition all of our data. So in the same way that the partition key is used to partition data across the cluster, we take the same partition key and use it to partition data inside a single node across different CPUs. Okay? We take different bits from the partition key, so there is no aliasing between a node and a particular shard. So that request path that I showed is actually replicated per CPU. And another thing that the thread per core design implies is that I can do blocking I/O. So indeed, all I/O that I need to do must be asynchronous. And nowadays, I think that with things like Netty, Node.js, and Go, people are used to having asynchronous network calls. Okay, no one is going to make a call over the network and block that thread for I don't know how many milliseconds. But the same thing happens with, for example, storage. If you're going to write to disk, what happens is that you're going to send a packet with, for example, a read command. That packet is going to go from the host machine to the disk controller. This controller is going to queue it. After a while, it's going to execute the commands, going to send an interrupt to the host machine, it's going to send the data back. This typically takes around 100 microseconds. There's a lot of latency involved here as well. And the same goes for multi-core CPUs. If you look at the diagram for like a Xeon server CPU, you're going to see that it looks very much like a distributed system. You have a lot of cores. They each have a chunk of the last level cache. They're all connected through a couple of rings. The rings are themselves connected by switches. And indeed, if you have a NUMA node, it takes like twice as many cycles to access memory on a remote NUMA node than it does on a local NUMA node. So we use message passing between CPUs to hide that latency. All of these asynchronous APIs are exposed via futures and promises. And I'll show an example later of how this looks like. Finally, we also have a user mode TCP IP stack. If you want to use the PDK for networking to totally bypass the kernel. This also brings a lot of performance gains. So here we see on the left a traditional stack. Happens to be that of Cassandra, but a lot of applications share it. And in this traditional stack, what you end up having is a lot of CPUs, a lot of threads that are multiplexed on a smaller number of CPUs. And you typically want to do this because when a thread blocks, it will be nice to have something else that's ready to run on that CPU, so you utilize it. And the problem is that this causes a lot of scheduler overhead. Okay, context switching between threads is expensive. It's hundreds of microseconds. And for example, you have no guarantee that you're going to select the correct thread to run, the one that will ensure greater forward progress. Also, the stacks of the threads are usually very deep, and they contain all of the context since the beginning of the request until this particular point in time. And that causes a lot of cache pollution. So you're going to lose all the data that a thread had cached. And that's not good. Also, if for some reason you have all the threads ready to run, because they are more than the number of CPUs, they can't all run at the same time, so we are just adding latency to a particular request. So in Seastar, we have something very different. There's a thread per core, and our scheduler, what it essentially does is it processes tasks. A task is just a Lambda function. Okay, it's usually very small, a few dozen bytes, and it basically glues together the completion of some I/O operation with the start of a new one. So it's usually a very small computation. So Seastar is essentially an I/O machine that's running a continuous loop, processing I/O completions and starting new I/O operations. And again, there are no locks. ScyllaDB runs without any atomic instructions. Everything's totally unshared. We have more applications using Seastar. We have our own version of memcached, which also performs much better, and someone is doing an implementation of Redis using Seastar. And it's, again, much better. They have a proper multi-core implementation of Redis. So this is how the programming model looks like. We're interested in futures, and the future in this particular example doesn't really have any data type, so it doesn't hold any value, but it's something that represents an asynchronous computation. So here we have a connection a network connection that we obtained somehow, and now we want to read 4 bytes off of it. And that function, read exactly, is going to return us a future. which will complete when those 4 bytes are available. So on that feature, we can call then to schedule a continuation, which is just the lambda function that we pass to the then function. The continuation is itself a feature upon which we can schedule a new continuation. So we can just chain continuations, right? And in this last continuation, you can see what I was talking about. We're just processing the end of the previous I/O, where we got the result, and we're starting a new I/O operation where we write the result to the connection. So if we look closer at that first continuation, what we're doing is mapping those 4 bytes to a particular identifier and choosing what CPU holds the data for that identifier, and then sending it a message saying, okay, look up this identifier for me. And the CPU will use its own local memories, its data structures, and it's going to do the lookup, and then it's going to return the result sometime after. And the message that we pass to the CPU doesn't even have to leave the cache subsystem, so it's very efficient. And in Seastar, all you do is you compose features, okay? You cannot leave the feature monad. You can't just call get on a feature, because again, that would block the thread, and we don't allow that. You can, however, have a green thread, what we call a Seastar thread, which is just your typical green thread implementation using set jump and long jump. And if you're in the context of a Seastar thread, then you can call get on a feature, and we will just switch that thread out and switch it back in when the feature is complete. And this is useful if you don't want to write code with all those features that are chained one after the other. Sometimes that gets hard to read, so you may want to have your code sequentially. In that case, you'll use a Seastar thread. But again, the Seastar thread is something that returns a feature, so you really never leave this programming model of chaining features. So yeah, here you don't really have any data races because everything is confined to a particular CPU, but you have other concurrency issues like reading some value, then going to do some asynchronous operation, and when you go back and use that value that you read before, it might be stale, so you might have what is called a check then act hazard. But it's more simple than concurrency in traditional languages. So we have our own memory allocator, which is not thread safe, and this is something that brings us a performance boost as well, because the system memory allocator has to take locks and doesn't guarantee that the memory it will give the CPU is that of its local NUMA node. So what we have instead is that we partition the memory in chunks and assign each CPU its own chunk. And this is very good for NUMA systems. Another problem with the system allocator is that it really doesn't have any built-in back pressure. So at some point, well, it won't even fail to give you memory. It will just give you memory, and if the kernel runs out of memory, it will just unleash the killer and kill your application. So it's not good. So what we have instead is we have a set of callbacks that we call when memory is getting low. And for example, Scylla will start evicting data from its cache in one of these callbacks. This is very similar to what the kernel does, right? When the kernel is running out of memory, it can't really abort because there's nothing to clean up after it. So the kernel can assume that an allocation is going to succeed. So the kernel has also callbacks that it calls when it's running out of memory, and typically what happens that memory will be swapped to disk, or things will be evicted from the page cache, or it will just start killing random user mode applications. And finally, if you want to share some data or transfer ownership of data between from one CPU to another, you can't really free that memory in the foreign CPU, right? Because all of the data structures are not thread safe. So again, what we do is we send a message to the original CPU saying, okay, whenever you can, free this block of data. So this is how Seastar works, and it's what underlies ScyllaDB. I mean, ScyllaDB itself we have a user mode scheduler, user mode IO scheduler. And what the problem that this is trying to solve is that when you have a particular device, if you throw more requests at it concurrently than the ones that it can handle, those requests are going to get queued. They are going to get queued in the device itself, they are going to get queued in the operating system's block layer, and on the file system layer as well. And there's nothing really wrong with queuing the requests because we can just throw them out, okay? So it's not a matter of latency. The problem is that we have no control over those requests. If we queue them in user mode, then we can do a lot of things. We can export metrics about how many requests are waiting to be serviced. We can cancel them if we can, or we can prioritize them. Because to the kernel, an IO request is opaque, but to the application, it can make informed decisions about which IO should be prioritized. Right? So another way to look at this is like a set of competing processes. You have the foreground process, like the query and the commit log, and you have a background process, like compaction. So and all of these processes have different priorities. So they each have their own queue, and what the scheduler does is basically a weighted round robin, where it will take items from these queues and send them to the device, right? And the priorities are not static. I'll talk more about this later, but they are dynamically adjusted. And the algorithm that we use is an exponential decay algorithm, so that if there is only one process using the device, then we ensure that it gets all of the bandwidth. So how do we know how many requests to send to the device so there is no queuing in between? Well, we do that by measuring. So when you are installing Scylla, the system will benchmark itself. It will start sending requests to the disk, increasing the number of concurrent requests, right? And as you are doing this, you can see that the throughput is increasing up to a point where it's going to reach a plateau, right? At this point, when you increase the concurrency, what happens is that the latency is going to increase linearly. This means that the requests are getting queued in those layers in the operating system. So what we do is that we record that value and use that to feed the IO scheduler and to define how many concurrent requests the device can actually handle. So we have an IO scheduler for disks, and we're working on a CPU scheduler to prioritize all of those continuations. And eventually, we want to have a network scheduler as well. So we have to be very careful with I/O, but the best thing, if we really want to optimize I/O, is to not have to do it at all. So systems like Cassandra and Scylla have a cache, right? In Cassandra, they use the kernel's page cache. There's a series of advantages and disadvantages to that. For example, the granularity is 4K, which means if you're reading a row that is just a couple of bytes, then you're going to bring along all of this extra stuff that you don't really care about and waste memory on it. So it's not really good. Again, the API, the page cache is thread safe, which again, we don't really need. Everything we have is isolated. And the API is synchronous, so if you do read or write, it's synchronous. There's no asynchronous version. The API is general purpose. The cache is general purpose. It's optimized for everything from desktop versions to server versions, which really means it's not optimized for anything in particular. We have a lack of control. We have two types of lack of control. Okay, one is that the API is fairly limited. You can do read, write, mmap, madvise, but you don't really have anything else. And we have lack of control because we don't own the code base. So if we want to change something in the page cache, we'll have to upstream that change, and it will be years before we actually are able to take advantage of it. On the other hand, it is there. It is written by very smart people. A lot of work has gone into it, and they take care of all the edge cases. So those are the arguments in favor of the page cache. So here is what I was talking about. If you have a very small row, but you read a bigger chunk, then you're going to have parasitic rows that you don't really care about polluting your cache. This is what happens when there's a page fault. If you do read and the page cache doesn't contain data for that particular page, then the kernel is going to block your thread, do all of the I/O, and when it's done, it's going to unblock your thread. So it's synchronous. And the page fault can take around microseconds. Cassandra, on top of the page cache, also has a couple of other caches, the row cache and the key cache, and it has different versions of them on and off heap. And you have tunables for all this, which is nearly impossible to get right. So in Scylla, what we have is we have a unified cache. And we can do very smart things here. We can have information on whether two rows are contiguous or not. So if there exists anything on disk between those rows or not. And that can save us a bunch of I/O. And our cache works in tandem with the Seastar allocator. So if we're running out of memory, those callbacks the allocator calls are going to get items evicted from the cache. Another thing that we can do is that we know precisely the hit and miss ratio of the cache, because we control all of it. So whenever we are bootstrapping a new node, all of its caches are going to be cold. So we don't want to send the same amount of requests to that node that we send to a node with fully warmed caches, because the latency is going to be impacted. Right? So what we do is we use the cache miss ratio for load balancing between nodes. Okay, we have an algorithm that chooses the probability of a request being sent to a particular node, and it takes into account the cache miss ratio and takes into account other things like it tries to minimize the network traffic. Okay, and the effect is that yellow line that you see, that over time the amount of read requests that a node is going to see starts to slowly increase. And you'll see a very similar graph for the cache hits of that node. So this is something cool that you can do, and it helps a lot if you're running on AWS and you have elastic EBS, where doing I/O is very, very expensive. So we have yet another allocator. So there are still problems with that system allocator that I talked about, namely fragmentation. So over time, as the workload changes and you start allocating objects of different sizes, you free them in a non-deterministic order, then you start to fragment your memory, right? And if you have, for some reason, to allocate a large block of memory, then you may have to evict a lot of items from the cache. So visually, this represents a set of allocations happening over time until we try to really do one big allocation and we run out of memory. So when we run out of memory, those callbacks that I mentioned are going to get invoked, and we're going to start freeing items from the cache. But the order in which the items are being freed depends on the cache policy. So it's going to be some kind of LRU. So we're going to have to free a lot of them until we finally have space to put that new block we wanted to allocate. And we have a bunch of holes now in the memory. So we have essentially decreased the effective size of the cache. So to solve this problem, we have an allocator that works similarly to the SS tables algorithm that I showed. And it basically gets memory from the Seastar allocator in big chunks. And then it takes one of those chunks and it does allocations on it. And the allocations are like in managed runtimes, just bump the pointer allocations, right? It just allocates at the tail of the segment. When the segment is filled, it closes that segment and it asks for a new one and it starts allocating there. So over time, as we are freeing, again, free is happening in an arbitrary order, we are going to be creating holes in all of the segments, okay? So what we do is we have a mechanism to compact those segments, okay? We have pick a segment, typically the most sparse, the one with most free space, and we compact it by moving that memory to a different place. Now, having to move around data in C++ is not the same thing as doing it in a managed runtime, right? So we have to teach the allocator how to move objects of a particular type. We have to do this per type. This typically involves keeping a back pointer, and when we copy the data to another place, then changing the back pointer now point to the new place. Okay. In some circles, this is known as garbage collection. We call it compaction. So it's not as nice as having the runtime take care of it for you, but in practice, we notice that most of the memory is used by the cache, and there's very small places where we need to have this special code with this allocator. Finally, like it happens in a manager runtime, right? If you're moving an object around, you pause everything, and then you walk the whole heap starting from the roots, and you update all of the references. We can't really do that in C++, so there are some places where we have dereferenced that memory that we want to move. So if we actually moved it at that point when we resume whatever task was using the memory, it will just now try to use memory that was freed. So in some places we have to take a lock, a non-blocking lock, saying that no compaction can take place. So it requires a bit of careful programming. Again, this all happens in the context of a single CPU. There's no coordination between CPUs to compact the memory. And we typically try to compact just one segment to satisfy the current request. So we don't spend a lot of time doing this garbage collection. Now, finally, workload conditioning is what we call the self-tuning idea, right? So this is basically having internal feedback loops that balance all of those different types of processes. So as a database, we export a lot of metrics, right? And we realized that we could just have the database consume those exact metrics and use them to tune itself. So for example, in Cassandra, you can configure the rate at which compactions should happen. But this isn't really good, right? There's no good value that you can choose, because if you choose a value that's too low and you're not doing enough compactions, then the number of SS tables just keeps growing and the reads are going to be affected. If you choose a value that is too high and you do too many compactions, then you end up spending a lot of the time doing that and not using the resources like CPU and disk for user requests. And the best values keep changing over time, right? Because they depend on the compaction backlog and they depend on whether we're doing streaming, for example, at the same time or not. So there's no static right value. So what we do is we have this generalization of the I/O scheduler that I showed before, which tries to dynamically measure the resource consumption from all of these different processes. And it will apply some control theory, or I guess deep learning now, that it's going to use to dynamically adjust the shares of those resources that each process gets. So for example, we have a controller for the compaction that is monitoring the compaction backlog. And if it is going to notice that we're starting to have a lot of SS tables that haven't been compacted, then it will adjust the priority of the compaction process, okay? So it gets more shares, and eventually it's going to throttle the online write requests. And the same goes, for example, for the mem table monitor. So we flush a mem table to disk when it goes above a certain threshold of memory. Now, if we notice that it's going over this threshold a lot, then it means that the rate at which we are flushing the mem table to disk is too slow. It's not keeping up with the volume of writes going to memory. And if we keep accepting all of those new writes, we're going to run out of memory. So what we do is, again, we adjust the priority, start flushing more aggressively, and this will have the effect of essentially bringing the system down to disk speed. So if we are working at memory speed, now we throttle things and go back to disk speed. And this happens until the system can catch up. So this is actually a very simple idea, right? But it's not trivial to implement. So those are some of the implementation details in ScyllaDB. We reach some conclusions. Like we saw, careful system design and control of your software can really maximize your performance gains. And you can do this with a lot of control without having to sacrifice latency. And you don't require an endless set of tunables from the user. You can do it all automatically. And of course, you can do all this while having a lot of fun if you like this kind of stuff. So here are a set of links that you can use to interact with ScyllaDB. I guess I failed to mention it, but we're totally open source. We're on Twitter, we're on Slack, we have a blog, we're hiring if you want to join. And that's it. Thank you very much.